Okay, everybody, we should be back now on the top of the hour. And most of us should be here. And if you have calendar questions, I can ask Tom to join us again. But now's your time to ask any questions for anything you didn't understand, and we can do our best to try to explain it. If not, we can engage into a research project to figure out what the answer might be.
I have two questions that are conceptual, so I don't know if I should go now or I should go at the end when other people ask more, run-of-the-mill questions.
Well, let's see if we have any questions, Ricardo. If we don't, then yeah, why not? So do you have any technical questions on anything we've covered in the tutorial, per se? You did such a great job of explaining things. Yeah, Nick, did you have a question?
Yes, so the fact that some of us are quiet doesn't mean we don't have questions. We have too many questions, as you can guess. But I also have sort of conceptual questions. So let me ask if I understand correctly. There were, at a certain point, there was mentioning that the mean molecular weight should not change with height or in time? In the atmosphere?
Both.
Both, excellent. That sounds very bad, isn't it? Because in real life, we expect stratification. And so, could you,
think of it as the heritage of the model, right? It's present day Earth. CO2 is fairly well mixed. And then the next most important thing that is varying is H2O. And also CO2 changes if you want to simulate, for example, 200 years of present day Earth, like past to future. CO2 might double, triple. It will not make any noticeable difference in the mean molecular weight that change. Then water is important.
Yes.
If you go to the tropics, you can have up to 2% of the atmosphere being water vapor. And this is significant. It does change maybe the third or a significant figure on the mean molecular weight, or maybe even the second just slightly. But this is something that we decided we are ready to absorb. And nearly every climate model is doing it like this, because it is still a small number compared to other uncertainties that climate models have. However, if you go to something like 10%, this change starts to become significant, because you have the water, which has a molecular weight of 18, and the rest of the atmosphere has a molecular weight of something like 28. Starts to become significant. At 10%, we're talking about, I don't know, maybe 10% also change in the mean molecular weight. It's quite a lot. So we have this number in mind that in general, something like a 10% is not acceptable, but a 2% is. So yes, it is important for present day.
I got that. Thank you. But the effect on the opacities, how this work?
That's different. Different. The opacity is a radiative transfer thing, and this is taken into account. So in dynamics, you need the molecular weight of the atmosphere. Yes. I think you don't need it in the radiative transfer. You need it. The radiative transfer needs distributions and calculations of concentrations and stuff, and you have that, and that is taken properly into account.
So it's not affected by the fixing of mean molecular weight?
No.
Okay.
Right. Radiative transfer sees everything. And he's right. If it's within 10%, we basically say it's okay. But we do have plans to fix this problem. And the Earth side of the house also wants to fix this problem, which means that it probably will actually happen. So
my second question also is connected to radiative transfer. Do we have radiative transfer guys here?
Eric still here?
I'm still here.
Okay.
Yeah, I'm here.
So the question is, what happens? I mean, you have some kind of opacity tables somewhere pre-computed. I don't know if there are fixed beans, where you calculate the opacity beans, where you calculate your radiative transfer, or something. Do you have them pre-calculated for different mixing in the atmosphere, or do you recompute that on the fly? You have multiple tables that you combine on the fly, or how do you do that?
So we have multiple different, we call them spectral files, that are tailored for different atmospheres and different mixtures that are described it's in one of the Google Docs, described for what they're tailored to. We can generally break them down into spectral files that are for Earth currently. Then we have our Archean Earth sets of files, which are nominally good up to 10% or so of CO2 and a few percent of methane. And there's several different versions there to parse through. And then we also have our Mars spectral files, which Mars and Paleo-Mars, which are for a pure CO2 atmosphere. So 100% CO2, but then with a little pieces of other things on the side, maybe some methane, maybe some H2, things like that. And then we have a few other kind of oddball sets out there that we're, in progress, working on and are up to date. There's a early moon set, but there we need to do I need to do some updating with the main Socrates with that. And then I'm also working on a hot climate, a Hadean set. So, but the three main working groups, I would say, are Archean, Mars, and then Earth. And so they do different mixtures we've tailored them for.
And somehow magically the calculation tests if there is no extrapolation in your tables, that the range of these trace species is consistent with what the model says. Over the Sahara, I don't know, too much dust or something. I don't know, something.
Well, this is something that's sort of the users. If you get a temperature violation, you'll get a warning that you're outside of the 400K upper limit on temperature. If you're using a spectral file, say you choose the Archean spectral file, one that's only good up to 1% of CO2, and you're running a Mars-like atmosphere, you're not going to get an error. It's going to, ROCKE-3D will run and it will give you a result, and that error will not be spit out by the model. So that's kind of under the user responsibility side of the problem that and you can always contact me and contact us about it, that you're using a spectral file that's relevant. So as I said in my spiel earlier, small differences. If the file says up to 1% CO2 and you use 2%, it's not a big deal. But if you're doing 100% CO2 and you're using a spectral file that says up to 1%, it's not good.
Obviously. Okay. Yeah. Thank you. Yeah. So that's.
I just wanted to add. I think the question was how it is done technically, and actually, Eric may correct me, but the spectral tables, they have actually the values for different partial pressures of different components, and I think also for different temperatures. I don't remember. So basically, radiation would sort of interpolate between like close points. So basically, yes, this information is there. I mean, if you have like completely different partial pressures of CO2 at different parts of the world, then different points from those lookup tables will be used for those parts of the world.
Yeah, got it. Thank you.
Okay, Jeff, you had your hand up.
I do. Thanks, Michael. I have, being a very, very newcomer to both this software and GCM modeling in general, I'm trying to get a sense of, I think it sort of leads from the last question as to whether the ocean models participate directly in chemical exchange. And so so just a moment ago, people were talking about what is acceptable spatial variations of composition of the atmosphere. And I am curious if there are spatial connections within the atmospheric model, or I'm sorry, within the ocean model, wherein the spatial variability of those oceans participate directly in buffering, say, of CO2 or water vapor.
I'll answer that. Nobody's answering. Yeah, right now there's no carbon cycle unless you enable it, and we typically don't enable it. There's people doing things along that line. I've done some Opacity simulations that involve changing the CO2 concentration of the atmosphere interactively, but that is not almost anything we do, which is just prescribing the CO2 concentration. So there's no ocean chemistry. It's just the physical ocean.
Okay.
And one thing to keep in mind is if you enable the carbon cycle, then you are severely tied to the Earth's biology and what we think that is. And you also increase your spin-up times by even a factor of 10.
Okay.
Yeah, about carbon cycle, I guess I would say that in Planet 1, you probably shouldn't do this. Planet 2, which will be released soon, it will have like all carbon cycle code that was used in our Earth simulations for CMIP6 in the comparison project. So it basically will have like latest and greatest Earth carbon cycle. But yes, it was mentioned. Biology is not usually programmed from like basic physics principles, but actually those are just empirical formulas taken from some observations on Earth and put it into the code. So whenever you depart from Earth conditions, you don't actually know what this code will be doing. So if you're modeling something that's completely different from Earth, then probably you shouldn't try to do anything like that. Except if you like want to put your own model for CO2 emissions and just use our CO2 plumbing functionality in the model, then yes, you can do this, but that will require some coding.
Okay, thank you.
Okay, well, no other hands up. Ricardo, why don't you ask your philosophical questions?
All right. So the first one has to do with the time steps in the simulation. So in other words, the time resolution of the simulation. So we've seen, for example, that there is this number in rad, that you set, say, to something like 5, which means every 5 time steps, you're going to call the radiated transfer routine. But those 5 units, those are units of what? What is the basic time step there?
That's DTSRC in the rundeck, which is a half hour.
Okay, so half an hour is the resolution of the model. That's what I wanted to know. And the second question, I mean, not the second question, but related to that, is that time allowed to vary dynamically or is fixed?
So the dynamics time step is fixed, but there are some model components that have substepping.
Right,
and that can be
dynamic one. It's fixed. It's half an hour.
Yes.
Okay, great.
No, it's not dynamics code. DTSRC that we are talking about, that's the main time stepping. That's basically, well, we call it like source time stepping, but that means basically the longest time step at which different components exchange information. So that's the time step at which atmospheric dynamics exchanges the information with column physics. Each of those can be run with different time step. So dynamics actually has also fixed time steps, but it is called DT in the run deck, and it's much shorter. I think it was discussed like yesterday. I looked at one of my run decks, and the shortest which I was using was like 50-something seconds. So it's much shorter than 900.
Oh, okay, so it's very, all right. Yeah. So the half hour is to check what's going on between different.
Yeah, it's, for example, you have clouds code. So you update clouds like only once per half an hour, because you assume that they don't change that quickly. And Dynamics sees the clouds, like gets information from clouds only once per half an hour. But when it advex stuff, I mean, when it does solves Navier-Stokes equation, it does it on much shorter time step. And you choose this time step. You have to choose it yourself, but you choose it based from the conditions of your models. Usually model would crash due to stability problems if your time step is too long, so you have to make it shorter. And land surface has its own time stepping. There is a multiplier for land surface, how often land surface wants to exchange data with planetary boundary layer. And also ground hydrology has its own dynamic time step already that is not feasible to any other parts of the model, but when you call then ground hydrology, it chooses appropriate time stepping, and it does it like a much shorter time step, and it could go to as short as 5 seconds if necessary. But land surface is usually fast, so it's not a big deal for it to do short time steps. So yeah, so it's kind of complicated, and
it's very useful to know. So from what you're saying, I would infer that the fluid dynamics of the atmosphere is going to have a resolution of about a minute. Things are going to be changed on a time scale of about a minute.
Usually it's longer than that. It's just an extreme case that I was running like thin paleo moon atmosphere, which was very thin, so the speeds are very high, and also it easily gets overheated. Usually I think it's like 400
450
something, like 450. Yeah, so that's I guess standard that is used for normal Earth runs.
But that's 450 what?
Seconds.
Oh,
but even with that, I think there are some parts in the dynamics code which actually do compute some time stepping dynamically. I'm sure. I'm sorry. I'm not a dynamicist, so I don't know all the details. But there are some places where actually a model looks at the conditions and decides like which time stepping should be used. But it's deep inside the dynamics. I'm not sure exactly for which algorithm it is used. But yes, there are some algorithms which use shorter time step inside the dynamics.
All right, so the second question has to do with this, the insulation at the top of the atmosphere. So, so this is really, okay, the standard conservation of energy number you see quoted, you know, it's, okay, you take the total amount of solar radiation that would be you would take from, say, the cross section of the Earth, and then you take that amount of power and you distribute it uniformly over the surface of the Earth, and then you come up with the usual 340 and excess watts per square meter. But how is this really being applied? For example, what is the height of the topmost cell of atmosphere that you are simulating, and what is that assume? What do you assume for that cell to be the amount of radiation you're really getting from above?
Well, I think so.
Go ahead.
Yeah. Well, I don't remember exactly what is the height in meters because we use
65 kilometers.
65 kilometers.
Yeah, we are using pressure coordinate system, so it's 0.1 millibar pressure where we basically cut our atmosphere for Earth.
0.01.
Point,
Point-
point, oh?
Yes, 0.01.
Okay, maybe it's 0.01. Yeah, I thought it was four orders, so it's five orders that we cut. We go through.
The 102 layer model goes to 1 order of magnitude lower.
Ah, you are talking about 102.
No, the 40 layer model goes to 0.01.
0.01. Okay, so anyway, that's how we define our upper layer. But
So
you-
for the upper layer, if I have this cell at 65 kilometer height,
Yeah.
Am I gonna be imposing that the flux of solar radiation for that cell? I mean, it doesn't make, given the time scale resolution you have, it doesn't make sense that I would assume for that cell to be receiving the 340 watts per square meter.
well, that's what your radiation transfer code is for. So the air there is very thin, so mostly it is transparent. So your radiation, it gets through the atmosphere and most of it gets to the surface. So basically, actually, the most of the heating of the planet happens through your shortwave radiation penetrating right to the surface. Surface is being heated up, emitting long wave radiation, and long wave radiation actually hits your atmosphere and also exchange of sensible heat flux between the surface and the atmosphere also heats up the atmosphere. The direct heating of the atmosphere by solar flux is not that significant. I guess Eric may correct me, but as I understand it, especially for thin atmospheres, it's probably, I mean, it's taken into account, but it's small. It's not the main thing. So that's why a radiative transfer code is crucial, because it basically does nearly everything for you. It heats up the atmosphere with shortwave radiation, but also it allows shortwave radiation to penetrate up to the surface. Surface emits long wave, and long wave again heats up the atmosphere. And on every time step, each parcel of the air basically is heated up by the long wave and short wave. We also compute radiative transfer also computes how much that cell will emit how much long wave radiation this cell will emit, and it will go both down to the surface and also up to the upper layers of the atmosphere. So emitted radiation by certain atmospheric cell, it will be then absorbed by the neighboring or like the next after it cell. So it's kind of like this interactive process, and only the layer of cells at the very top of the atmosphere, they just emit radiation directly to the vacuum, and that radiation disappears basically. And that's since the atmosphere is very thin there, that's a very small part of the radiation, but it's taken into account. But when we are talking about radiation at the top of the atmosphere, we mean the sum of the radiation transmitted emitted by everything that is below that upper layer. So it's surface plus all the cells in the atmosphere, everything that was not absorbed by the atmosphere, and that is emitted into the space. So that's the top of the atmosphere radiation that we are talking about. I don't know if I was clear or.
No, I understand what you're saying, but I don't think it was the question I was trying to understand, which is this average number that you typically see quoted, the 340 watts per square meter. That's just conservation of energy you apply because you say, okay, the Earth, I think the cross section of the Earth I know the luminosity of the sun at the distance of the Earth. I get a certain amount of energy that will be, I assume, will be completely absorbed. And then I say, well, the atmosphere will equilibrate. So I take all that radiation and I now spread it over the 4 pi r square of the surface of the Earth, and that's how I get my 340 watts per meter. That's, yeah, very solid is conservation of energy, but that's very simplistic for the kind of sophisticated model you have. So that's why I'm trying to understand.
But Ricardo, that's not done in the there's no such averaging done in the GCM. Everything's done at, if you took a 15-minute snapshot of where the sun is and output that net CDF file and looked at the top of the atmosphere of sunlight, you would see the correct spatial distribution of sunlight. The averaging is, there's nowhere that's done. That just is what emerges when you do the averaging, but that's not done. It's not like the sun is fixed every time.
Yeah, right. That's why I was trying to understand why this number appears all over the place, but the model clearly is not making that assumption.
Well, yeah, it's not making that assumption. I mean, you see that number quoted because, I mean, why do people quote the average of anything? It's useful, but it's not how things are done at the time step level in the GCM.
Okay.
Okay. No, this number is not included anywhere as input or anything. The only number that we include is the insolation from, I mean, the amount of energy that comes from sun per meter square above the Earth, and that's 1,300 something watts per meter square. So that's the only input that we actually need. Everything else is computed, and if you refer to other numbers, that's something that was computed, and some averages that have been taken.
Okay, so let's, I think Trent has his hand up. So Trent, can you ask your question?
Yeah, can you hear me?
Yep, we hear you.
Cool. So I'm interested in a lot about modeling like the outer edge of the habitable zone. And I remember yesterday, Michael, you mentioned how that's where you can run into some problems with the ocean freezing to the bottom. And I was wondering if you guys have studied this before and stuff, and just how big of an obstacle that really is, and perhaps some ways you've been able to work around it or get close without crashing the model, I guess. Yeah.
Well, there are there's a lot of issues to unwind there. I would say the key way that we have tried to succeed in the past was to make the oceans deeper. That's why we use those bathtub oceans we talked about earlier, where we make the continental shelves much deeper, because if you look at Earth, some of the continental shelves are very shallow. If you move Earth out to Mars, those continental shelves will freeze at the bottom extremely rapidly. So to avoid those kind of issues, we build these bathtub oceans, and those could be made deeper as need be. But you have other issues that can take place as well. For example, Mars receives so little insulation that CO2 can condense out of the atmosphere. And we have the ability to handle some of that in Planet 2.0, but we don't have a way to change the mean molecular weight of the atmosphere, as we've discussed, as the CO2, if it's a major fraction of the atmosphere, condenses out. So you have to be very careful when you do outer edge of the habitable zone studies with this model, to be careful that things like that aren't happening. It depends on what your atmosphere is made out of and what you want to model. Probably the easiest way to do outer habitable zone modeling is to do some of the stuff we've done with Mars that Igor Leonov has led, and our colleague at Goddard, Scott Guzewich, and myself have done some ancient Mars modeling. But that's mostly dealing with either land planets with small water vapor reservoirs, so no oceans, or oceans, but we give the atmosphere some powerful greenhouse gases that have been theoretically estimated from various theoretical studies like H2. But to do outer edge of the habitable zone is very difficult. So we haven't done that much of it because it's a difficult problem to solve. And we won't be able to solve it properly until we address these issues with our ocean and the issue of these condensable species.
Yeah, if I may, Mike.
Yeah, please.
We have a new hire on the Earth modeling side that's going to restart to work on the surface type. So right now, when as Mike explained, when the ocean freezes to the bottom, the model basically crashes. But ideally, you would want to convert this column of ice into land ice. And so that this new person will be working on this, and this will be work that will be transferred to to ROCKE-3D. So in a future version of the model, it would be, I guess it would be much easier to run planets that are on the outer edge of the inhabitable zone.
But just to say, nothing like that will happen anytime soon. Because just as a caveat, I mean, Tony's right that we've hired somebody, but we have hired other people in the past who accomplished nothing in this domain. So it's a difficult problem to solve, and it has not been solved yet. So even if we got a good person, which we don't know yet if this person's super great or not, it will not happen within the next year, I would say. It's at least a year.
I guess it's not clear what we are talking about. We are talking when we are talking
about the ocean freezing to the bottom.
No, that's one thing. But also, this person was hired, I guess, for land ice modeling, and that's another problem with outer edge. That if you have big water reservoirs, like if you have ocean, then it's a source of water which will basically migrate to cold regions. And since we don't have dynamic ice, you will just keep piling ice indefinitely. So you will grow like huge glaciers in certain cells, like many kilometers high. And we don't have functionality to remove this water. I mean, we have this kind of hackish functionality just to assume that this snow should go back to ocean if it becomes too thick, but that's kind of like not what really should happen in the real world. So that's something that is still missing, and we will be working on it. But yes, keep in mind that if your planet is too cold, then it will be accumulating a lot of water. I mean, a lot of frozen water in certain areas, and that water will not move. So it will be there.
Can I just add, if you're doing exoplanet outer edge stuff, a lot of people use aquaplanets for these kind of things. So you're not going to freeze to the bottom or accumulate ice sheets. So you won't have any problems other than this if CO2 condenses. If you're in that regime.
Chris, that's not true. You can freeze at the bottom in an aquaplanet at the outer edge. It's no problem if it's cold enough.
Sure, you can. But if you have a 1,500 meter deep planet, your climate's going to stabilize well before that happens.
Yes.
And so, but
that's a good point. Because that's what I was saying. We deepen these ocean cells in some of these models to see if we can reach net red planet within the bounds that we're interested in. If we do, even if the planet is not in hydrological equilibrium, we declare victory and we move on. So as Chris is saying.
Mike, can I add sort of a philosophical point?
Yes, please.
If you'll indulge me. Some of you may be listening to this and you might feel a little negative that like, oh, can we do hazes? Oh no, we can't do that. Oh, can we do meteor impacts? Oh no, we can't do that. What about the outer edge? Oh, it's difficult. Don't let that stop you. We're all time limited, and we know, and I think this is a good, all these interesting problems that come up are indicative of how many really cool problems there are to do. And if you're, a student and you have a really good project idea, like we know a lot about the model, and we'd love to talk to you and help you if you have the time to pursue some of these awesome ideas, which we are just too busy doing our thing. As getting older as being scientists, where you do more and more administrative stuff and less being able to focus on a really cool project. But we'd love to work with people if you really have a passion and you want to attack some of these problems. And we're saying, oh, well, there's issues that need to be resolved. We'd love to work with people to try to help get these issues resolved and move the model forward. So don't let us, like our kind of pessimism at times of, oh, that's going to be hard to do. Don't let that stop you. where there's a will, there's a way, and we can be a good resource in trying to help you figure out some of these details about how to do these harder problems. So I'll end my rant there.
Yeah, but definitely talk to us first, because we don't want you to go down to a dead end. You know, you ran a simulation for 3
Agreed.
months and they all went nowhere. And we would probably know if they will go nowhere before you run any of them.
We are all, sorry, we're all here because of these possibilities.
Yeah.
Yeah, so.
Absolutely.
Yeah, thanks everyone for the answers. My main takeaway is that this is a really interesting area for progress. So nice.
Thanks, Trent.
Yeah, but I should also mention that a lot of progress was done on outer edge, and CO2 condensation, it will be available in Planet 2, and that's one of the basic things. At the moment, you can condense only you can condense CO2 only at the land, and there is a still problem condensing it on the snow, which I'm currently working about on, so maybe it will be resolved by the time we freeze Planet 2, or at least it will be resolved in like next generations of Planet 2. Like so basically, yes, if you have only, I would say, CO2 and water in the atmosphere, then yes, you can condense both of them. So at the moment, you cannot condense too much water and CO2 at the same time. But that will be fixed. And even if you have certain other elements, if it's not much of it, like if you have argon on Mars, there isn't much of that. So it actually doesn't change atmospheric molecular weight too much. So you may still get away even with putting argon into the atmosphere. We didn't do this, but that doesn't mean it's absolutely impossible.
Yeah, and of course, the mean molecular weight atmosphere won't be an issue if your atmosphere is pure CO2. It can condense out, it's no problem.
Yeah, pure CO2, that's what we started from, and that's working.
Exactly. Okay, so Stephen, you have your hand up. Go ahead.
You didn't directly address it, but in the straits file, there's the location of the grid cell, and then there's a D number after it. How does that relate to reality? I know it somehow defines a position inside the cell, but I can't quite figure it out.
I do have some documentation somewhere exactly how it works, how those different coordinates tell you from which part of the cell the flow goes from to the other. But you don't have to have that file. The straits are only if you think that you want to have water flow between two disconnected ocean grid cells, basically. So let's say you have two land grid cells like this and you want a strait to flow through them, then you can set that up, but it's not required by the model in any way. And probably for an exoplanet, it would be kind of strange to use it because you have no idea really what the topography of it. You'd have to make some assumptions. You'd have to make assumptions about the depth of the strait. And those things are probably not going to, unless it's a major component, it's not going to affect your climate, your global climate so much in a sense.
All right, then I have a real softball question for you.
Sure.
Why is the resolution 4 degrees by 5 degrees? Why isn't it 4 by 4 or 5 by 5?
Well, it's because it's fast. That's why we run the 4 by 5 as our workhorse model. And that's partly because there's so many uncertain, I mean, we're mostly thinking in terms of exoplanetary studies. So there's so many uncertainties already in the exoplanetary realm. You know, we're not going to have a directly imaged, high resolution image of a exoplanet in our lifetimes. So there's great advantages to run by 4 by 5 because you can reach equilibrium much more quickly than you can have in a high-res model. But at the same time, in Planet 2.0, we are going to have the option to run 2 by 2.5 lat long grid cells and 1 by 1.25 ocean grid cells, if so desired. So that will be an option, and that is the same option that the Earth climate model is using at present.
I guess the question was why our cells are not square, but like.
Well, I don't know. Ask him. Is that your question, Stephen? Is that why they're not square, or was it the size you were asking about?
It was the fact that they're not square. That was the softball part.
I see.
Yeah, but basically on the sphere, it's difficult to choose. You want to choose cells which actually would be more or less square, but if you go to poles, they become more narrow, and when you go to equators, then they become more like wide. So I think that taken slightly like longer in latitude and longitude direction, so that basically when you go to poles, they become like less narrow. But it's kind of, I guess it comes with community, and I don't know, people have been making these decisions for a very long time for different architectures and for different models, and somehow it just happened that they settled on certain like common resolutions which everybody is using. So yeah, it's no,
So-
usually, yeah, you don't have to use 4x5, but it just happened that the community uses it a lot.
So there is also the thing that just because the planet rotates on the longitude direction, having a longer dimension in that longitude direction makes more sense, because it is the more uniform direction. If you go across latitudes, just because Earth is a fast rotator, the latitudes differ. The different constituents differ a lot by latitude, but not so much by longitude. And the Earth flow is like this, and it is in general. It makes more sense to have the longitude dimension longer. And in my previous lifetime, when I was a postdoc in Paris, that I was using the LMD model, back then their resolution was 2.5 by 5. So it was like having two square boxes across the longitude direction as one box. And they were claiming that they have tested different shapes, and that was the optimal one in terms of performance and accuracy. I have never seen those tests myself. I didn't care back then about that. But that's just one extra piece of information. But it is indeed true that for either by chance or by some very valid reason, what Igor is saying is right. The shape of the boxes are throughout the community about that ratio of lon versus lat.
Makes sense to me. Thank you very much, everyone.
I should also mention that people use other grids, and for example, in version 3 of the model, we hope to have a cubed sphere, what's called, that's basically what is already used in our mother model, Earth model. And there, basically, you have cube sphere is basically when you put a cube inside this inside the sphere and then project your sphere onto that cube. So in that case, all your you choose cells basically by dividing faces of the cube into more or less equal equal rectangles. So basically there, I guess you would not see this difference between latitudinal and longitudinal dimensions, but the cells will still be not equal because you cannot make all cells identical on the sphere. So it's also some approximation, and I guess there are also different ways how people project a sphere to the cube. It's another field.
And also those grids cell schemes can be more computationally expensive, because typically you put a core per grid cell. Right now we put a core per latitude. So you need a lot more cores for these, especially if you go to something like an icosahedral grid. Again, this is another kind of.
No, you always use the number of cores that you have. I mean, cube sphere just allows you to use more cores. So actually your jobs are faster.
If you want to use it, but if you want to, but if you want to run it efficiently, you put a core per grid cell, obviously, and then it will run.
No, because if you put a core per grid cell, then the communication will kill you. So usually you have always several cells per core, but that's another science. I mean, and it's also changes depending on which architecture you're using. So if yes.
Okay, that's what I've seen somewhere else, so that's kind of
Well,
but anyway.
it depends on how expensive
so,
your algorithms are. If you're wasting like 90% of time on radiation, and radiation is basically a single column model, then yes, you use one core per cell. But if it's dynamics, then it's other way around. So.
Okay, so any other last questions? If not, we'll end things here. Okay. Well, great. Thank you all for joining us then for this year's tutorial, and I'll send out a link to the YouTube recordings. I've already sent them to our webmaster for yesterday, and he's already gotten those uploaded onto our YouTube channel. And we'll have these up there as well. So you can always go back and see what sort of things you might have missed. Otherwise, you have our contact information. If you have more questions, feel free to write us. Of course, we're busy as everyone else. We're all working scientists as well, as you might imagine. So if it takes us a while to respond, you'll know why. Anyway, so thank you all for joining us. And also thank you to my co-hosts. Thank you to Chris and Kostas, Igor, Eric, Tony, and I think Geronimo and Tomas may not be here, but also Tom. All been really useful this year. Thank you so much, everybody. We'll be around.
Thank you, guys.
Bye.
Bye.